Okay, hi everyone, how are you doing? Okay, so my presentation is going to be fairly similar at the start to what Daniel just went through. And also my introduction is going to be fairly similar as well. I also worked at NI for 2 years. I'm a CLA and CPI, Certified Professional Instructor. And today I wanted to give you a flavour of what I do on my day-to-day work now at Scientifica, which is typically with object-oriented programming and actor-oriented design. So at Scientifica, I produce control software for multiphoton microscopes like this. And for our users, they see a variety of different aspects with our microscopes. So the first thing here is that there's lots of moving parts on the microscope. So the bottom stage here, that can move around. And so our samples, which are typically neurons, can move with nanometer precision. We have some micromanipulators here. We have an objective that can change the magnification shining onto these neurons. Now, because depending on our sample and the type of neuron we are using, we need to carefully control the temperature on our sample plate here. And then there's two types of light source that we use. The first is illumination, so how we actually see our sample. So we typically shine an LED from the bottom through our sample, then we can view it at the top. The second type of light source is for stimulation. And to do that, we typically use a category 4 laser, and we shine those onto specific neurons in order to stimulate them. And with all work with lasers, we have to control lots of laser optics. An alternative approach is an epifluorescent LED, where you can stimulate the neurons with wavelengths anything from ultraviolet to infrared. And you can also change the intensities of these different wavelengths. We have a camera at the top to see how our neurons are responding to different stimuli. And of course, the user needs to be able to control the application, control the microscope in some way, so we have a graphical user interface. Now, these sorts of devices are used in industry, in academia, and no two experiments are the same. So all of this has to be fully configurable. So this is what the customer sees. Behind the scenes, I've just picked out 4 main processes that I have to work on. So the first is I've just put XML up there, where we have configuration, different configuration file types. We have lots of vision processing that we need to do. User interface items such as trees. And for motion stuff, because everything is fully configurable, we can have n number of motion devices. So when I'm developing software at Scientifica, I need all of my code to be maintainable, scalable, debuggable, reusable, distributable. And as a CPI, if I've ever taught you before, you've heard me say all of these things several times, as you would have done if you've been to any NI course. Now, the #1 way that I found of achieving these items is the use of object-oriented programming. Okay, so this is where we're going to start having quite a big overlap with what Daniel went through earlier, but I'll be expanding on what he said. So I want to start off by saying what an object is. So people go through life and we see objects every day, and the way that we as humans would define an object is anything we can know something about. So for example, I have a bottle opener here, and this is my bottle opener. The things that we need to know about these objects are a name or an identity. This here is a bottle opener, that's its identity. Next, it has properties and attributes such as owner, weight, size, shape. And then lastly, I need to do things with this object, such as here, opening a bottle or opening a can with the lever. So objects here are individual items. Now, I didn't need to read a programming manual on how to use this bottle opener because my mind classified this into a generic group. And that generic group told me what I could do with this bottle opener and what I need to know about it. So classes can define the data and the actions of an object. I must admit, I didn't expect the screen to be this big, so I'm sorry if this is hurting your eyes a bit. Okay, another definition we could give this is that a class is a custom data type and the methods that interact with that data, then an object is an individual instance of a class. So in LabVIEW, we might have a bottle opener class. In G, we can use that individual object, we can give it data, and we can perform processes. This is a bottle opener. There are many like it, but this one is mine. Okay. Let's start with an actual example which I did a couple of weeks ago for work. Now, I wanted to build my configuration files based on an XML format. But I very quickly realized, okay, using XML in LabVIEW is surprisingly difficult. I didn't expect XML to be as difficult as it was until I started using it. For example, here, this, as you can tell from my expert icon, is just to insert a new line into an XML file with a couple of attributes. But to do that, I have, 5 property nodes, and I need to work out which references I need for which property node, for which invoke node. And so I thought, okay, I'm going to build an API to allow myself and my other developers to use XML. So I had to look at what I wanted to be able to do with XML. And typically with files, I wanted to open or create. I want to pass some data within the XML file, so read or write data, and then save and close at the bottom there. The attributes to this XML file in LabVIEW, well, you just have the one if we're using LabVIEW, and that's a reference, or a DOM, document object model. So I created this class. Now this class has private data, as Daniel went into earlier, and the only thing in my private data is a document object model, and that contains everything I need to actually work this XML file. Underneath there, I have my list of methods, and I decided on my list of methods before I created this class. Now, this shows the definition of a class that I gave you earlier, where a class was a custom data type, which we see here, and the methods that interact with that data type. So from here, I was able to create a very straightforward API, where to read a value in an XML file, I could just open a file, search for a particular piece of data. Here I'm just outputting the entire XML file, and then close that file and check for any errors. So these 4 items can replace the hundreds of invoke nodes that you would have to use without this API. Okay, so one of the aspects of object-oriented programming that I've used here, that Daniel gave me a great introduction for, is encapsulation. So the methods I've used in the XML class, there isn't a method called getDOM or getReference. Instead, those methods use the reference in order to achieve a particular task. So a class bundles the methods with the data to perform actions, and that's encapsulation. Okay, now, yeah, so we've encapsulated the methods here with the private data of that class. Now, the key thing here, again, what Daniel said, is that this private data, well, it's private, which means no other VIs can actually access this XML data. Now, that's important when coming back to how we want to make our code, because let's say we have a bug somewhere in our application. If the bug is to do with an XML file, then that's okay. We know that the only items that interact with that XML file is the API that we created. Also, with that API, because each method is doing one particular task, our code is inherently testable. If it's just doing one particular task, we can create a unit test for that class, and at Scientifica, we use the unit test framework. And I'll talk about scalable and maintainable a bit later on. But distributable and reusable, I'll just touch on distributable very quickly. And what I've started to use a lot is the JKI package manager. Now, you don't need to use OOP with this. The JKI package manager will just turn a folder of functions into an API that you can put in your functions palette. But using OOP, it lends itself very nicely to becoming an API. So I created a VI package, which installed onto my functions palette, and also I could include different examples to show the other developers at Scientifica how I intended my API to be used. Okay. The second example I wanted to give was actually test result data. So within the area of neuroscience research, different customers have different needs. For example, PhD students tend to want an easy-to-use file format such as a CSV file or an Excel file. Our customers within industry tend to use different TIFF configuration files. However, when writing the code, there's no way of knowing which type of file your customer is going to be using. So we can use a concept called inheritance within object-oriented programming. Whereas we have a results file right at the very top of our tree. Now, there's no such thing as a generic results file, so we can call that abstract. It's an abstract class. And on the board here, this is just an example of a UML diagram where we have the name and identity, the properties or data types of our class, and also the methods or attributes. As we go down a level to our child classes, we can say that, okay, a CSV file, Excel, and TIFF file need to have all of these properties. They inherit all of those properties and the data associated. However, the way that we open an Excel file is going to be different to the way we open a TIFF file. So we can override the parent level open file method. So to give just a bit of an example in LabVIEW here, I've taken 3 of the classes of results file, CSV, and Excel. And from this parent class here, I've just dragged and dropped a couple of the methods, such as open file, write data, save, and close file, as well as a notify user method. Now, here I've just put an example of how you can choose between 2 different objects in G, or on your block diagram. So let's say the user wants a CSV file output, they can put true here, and a CSV object gets passed through. Alternatively, if they want an Excel file, they can have false here, and the Excel file is passed through. And depending on the object that's passed through, these methods are going to change. However, just because we're using object-oriented programming doesn't mean we have to change the properties here. So the top methods here, we're going to call those dynamic dispatch methods because they're the types of methods that can change depending on the file format. Your child classes can then choose to override those methods. And then the last type of VI we have on the screen here is a static dispatch method, which is this one here, of notify user, because regardless of the type of object or type of file you want to use, the way we notify the user is going to be exactly the same. So we can have a static dispatch method which is going to execute regardless of which child class gets passed through. So just as a quick recap, inheritance allows new classes to reuse the properties and methods of a base class, also known as a parent class. And the new class may choose to change or append the behavior of properties of the base class. And that's inheritance. The last pillar which Daniel spoke about earlier was composition. Now, I've very recently architected some device drivers based on composition because I needed to create a scalable piece of software. Because at Scientifica, our customer requirements are unique for every customer. It has to be very configurable. And also, the drivers here have lots of different configurations in themselves. So some of my aims were to provide a clean API to control all devices that interact with microscopes. I needed device controllers can change, and also the way that our PC communicates with those controllers can change as well. So hardware interface support can change. So with this in mind and what we know about inheritance, I started off by creating a device class hierarchy. So here we have devices, and underneath devices we have different items such as motion devices, optical devices, cameras, and temperature controllers. With inside there, well, we have the individual items that can move on a microscope, such as a stage, a micromanipulator, an objective changer, and different axes, such as a Z condenser. Now, these devices, these are what I want the developers to be using at Scientifica. But behind the scenes, each of those devices needs a driver. And the driver used is going to change depending on which physical, maybe perhaps PXI card or PCI card you have connected to your PC. So it could be a Scientifica-made motion card, it could be a motion card from National Instruments. But the point is that the developers should be able to use the same API for any type of motion card. Then lastly, these drivers need to interact with the outside world. So I created a communication class, and that can swap between, in this instance, just TCP/IP and serial. Now, because I've structured it like this, I can now use a technique called composition, where I can link these three class hierarchies together. Now, what I'm saying here is that a device has a driver, and a driver has to communicate. And if we were to zoom in on the private data of a class, such as such as the driver here, you can see that we have a communication object inside that private data. And if we looked inside devices, we would see a driver's object inside there. So this allows 2 stages of configurability from the developer side or the customer side. So the developer can use any of these, well, can use this API. That API can then configure what type of driver we're using. And then the driver can then decide, okay, whether it's serial or TCP. And so the use of a class within a class you can call composition. Okay, mind your eyes slightly. Okay, so just a quick recap of what we've gone through so far is a class is a custom data type and the methods required to interact with that data type. And a collection of objects can be represented by a class. An object is an instance of a class, and you might have heard the phrase, the wire is the object. Next, encapsulation bundles the data and the methods that operate on that data together. Inheritance allows a new class to reuse, change, or append to the properties and methods of a parent class. So we could say an object is a type of another object. And then lastly, composition allows a class to use another class, or an object has another object. Okay, so using these principles of object-oriented programming, well, I created a couple of reuse libraries, or APIs, such as the communication suites here, XML device tree that I mentioned as well. I also have an error handler there. Okay, now what? Well, now that we have these reuse libraries, we actually need to put them into an application. Okay, so Fab showed us this a bit earlier. It's the acquisition and logging sample project that comes with LabVIEW. Now we can see here that we have multiple loops or multiple processes. And after a bit of research as to how the programming community as a whole, not just within our LabVIEW world, would describe this sort of design pattern, so not just a queued message handler, but we have persistent modules. Our modules encapsulate internal states, and all of these modules are asynchronous. So what do I mean by persistent? Well, all of these processes here exist when we tell them to exist. In this case, just when we load main VI. And they die when we tell them to die, or rather destroyed, when we tell them to go. This is unlike, let's say, a thread model, where a thread only exists when you're using it. We're encapsulating internal state. Yep, well, there's 2 things here. Let's take this message handling loop. The different states here represented by the case structure, and also data can be sent around the different states in our case structure by the use of these shift registers on the side. Now, for me, the queued message handler, like you see here, was the gateway drug to the actor model, or actor-oriented design. And I've put a definition here of a C-based programmer who I follow on YouTube of the actor model is a method of concurrency in which the universal primitive is an actor. So by concurrency, just essentially saying asynchronous. So different processes can do different things at different rates. And there's no data dependency between them. And the primitive of being an actor Well, typically we can define an actor as a process which is persistent, encapsulates internal state, and is asynchronous. Now, there's a couple of other things which we say actors should be able to do. So they are to launch a new actor or create a new actor. They should be able to receive message requests, and in response, they can choose to make a local decision, and that decision can include to just ignore the message completely. They perform actions and they send messages. They process exactly one message at a time. And the way that we communicate is actors do not communicate by sharing memory, instead share memory by communicating. So it's just another way of saying that in the actor model, we don't use things like CVTs or lookup tables or other types of data sharing mechanisms, apart from the communication mechanisms that we use. So I said that earlier that the QMH was the gateway drug to the actor model. So if we go back to the QMH here, and now thinking of all of these processes as different actors, probably excluding this bottom one here, we can say that, okay, this QMH has the ability to launch new actors. There's the asterisk here because, well, here we're launching a synchronous process, but imagine we had the asynchronous call function there. We can perform local decisions and actions. An actor has the ability to send a message, and a message we're going to define as an instruction and the data to execute that instruction. We can process exactly one message at a time, and in LabVIEW, we all do that via queues. And we share data by communicating. So any message that we send in a QMH, we can send any type of data that we want via a variant. Okay, so coming back to this screen which I showed you earlier. Well, a QMH, yep, is scalable. If we want to add new processes, we can add in new loops if we wanted. It's maintainable in the sense of all of the functions are there within case structures. If you want to add or append the code, you can do. Let's say we used the queue's message handler with object-oriented programming for your state data. I've already spoken about debuggable and testable. We could distribute them, like I showed you earlier with the JKI package manager. However, our code is not reusable. If we have a loop in the QMH, so let's double click on the acquisition loop here. There's no way that we can actually use this code in other applications. Not on its own anyway, because this particular piece of code is just judging by the reference inputs there, has to be used with 4 other loops as well. And it's something that Fabiola picked up on earlier. Now, I'm a really lazy programmer. I only want to create code once and reuse it as many times as I can. So if we were to restructure this message handling loop, we can, well, strip out all of the functionality, so we're left with the bare bones of dequeuing a message, performing an action. We can send a message if we want, and we also have some error handling at the end. Now, in the case structure, we are performing an action, and we can interact with the data that's running along from our shift registers, but the action we are performing is going to change depending on the data that we send to its condition terminal. So if we want something to change functionality depending on the data of what we wire to it, well, we could look to object-oriented programming for the solution. So the use of, here I've put down an example of the command pattern, where depending on the object that we send a VI, we want that to change functionality. So here we have a piece of code where we are enqueuing an initialization message. Then inside our message handling loop here, we are dequeuing that object, and based on the object that we dequeue, well, this execute command is going to dynamically change to whatever was held by this object. Now, my chosen framework at Scientifica, I use Actor Framework 9 to 5, 5 days a week. Now, that's because Actor Framework is based on the command pattern. So looking at the previous slide where we are dequeuing an object and we have a dynamic dispatch VI here, which will change depending on the object being passed into it. Well, that's exactly how actor call works inside the actor class, the top level class for the actor framework. So here we have a dequeue message VI. We have a receive message VI here, and inside there, as Alan showed us earlier, we have a do VI, which is a dynamic dispatch VI. So depending on the object that we send that do VI, we are going to perform different actions. The actions which are shipped with the top level class include these 5 here, including a stop message, which we use for every single application. Also included is an error handler VI. And again, that's dynamic dispatch, so we can change the behavior of our actor here to change how we respond to errors. To help us get started with actor-oriented design, specifically looking at the actor framework, shipped with LabVIEW is the coffee shop example. Now, this is how I got to grips with how to use AF in LabVIEW. The idea behind this example is that we have a coffee shop. So let's start off with a coffee shop actor class, which we see here. Now, that coffee shop needs a manager to work out who should make which coffee. So you can call that a work dispatcher. And then that coffee shop needs some workers. So we have a worker class here, because there's more than one type of worker. So a child class of worker includes a barista and a cashier. They're 2 different jobs, but they both have to work, hence why we call them workers. And then we have customers. Now, customers, for the most part, are very nice. They walk in, they get their coffee, and they leave. Others are a bit rude, and they might go in with their cell phone. So we have the option here of creating a customer who's nice, or creating a customer with a cell phone. Now, this is a class diagram. And remember that classes just tell us how many, a class just defines how we want objects to behave. But we could have as many objects as we wanted. So typically we would have 1 coffee shop and 1 scheduler. But we could have n number of baristas, cashiers, and customers. Now, all of those instances within a coffee shop, well, they're their own unique process. Now, the nice thing here, because actor class has an actor core, which, by the way, is a method, a dynamic dispatch method of the actor class, well, we have data here, which can be shared along the different states, but also, because it's a dynamic dispatch method, well, that method is propagated through down to the bottom levels of this class hierarchy. So no longer do we need to create a VI, put down a while loop, case structure, and queues, because it already exists in the actor class. So every child class can inherit from it and use an instance of this actor core. Next to the actor class on this tree, we have a message class. Now that message class, remember, the message is the object which we pass into our receive message VI. And the sub-VI within there will change depending on the objects that's passed through. So every message that we want to send between these individual processes or individual actors will inherit from message class. Now that's fine, because as Alan spoke about earlier, that's all been scripted for us. So if we have a method such as add a barista, that's fine. We can tell an actor to add a barista by right-clicking and creating a message. That will create our message class for adding a barista. And so long as we have the reference, we can then send this particular actor, which is a coffee shop, this instance, and tell it to add a barista. Now, Actor Framework, although it's my favorite course to teach, there's quite a lot of it. So there's quite a lot more to this. But for now, I was just going to say thank you. And there's still a bit of time left if you want to ask any questions. No one? Okay.
I've got one here. Hey, is there a benefit to embedding the classes inside another class as you had? Or can you just call from the same level?
With composition,
Yeah.
you say? So I use composition to separate my class hierarchies into different code reuse libraries. I also do that because I think it's a trap for young players to use inheritance as a way of generalizing classes. So you can use inheritance, but you can't say that a driver is a communication protocol. A driver uses a communication protocol, and the communication protocol that it uses can change. Perhaps I want to use Ethernet instead of serial, which is why I use a composition.
Yeah, thanks.
Just going back to Alan's point earlier about learning Actor Framework, was Actor Framework something you learnt quite early on in your LabVIEW career, or is it something that you learnt all the other frameworks and then Actor Framework was the last, and how did you get on with that?
Well, I think, as I said before, before I started at Scientifica, I worked at National Instruments for 2 years, where essentially my job was to learn LabVIEW. And so I started learning Actor Framework at the second CLA summit I went to. And yeah, I think as Daniel mentioned, I learned Actor after I got my CLA. I was fairly comfortable with object-oriented programming. But yeah, I thought that Actor Framework was a nice progression to essentially Core 3 and OOP.
Did you do the course, or did you just... sorry, have you done the Actor Framework course, or is it just something you learned organically?
Yes, so I self-paced the Actor Framework course. I also teach the Actor Framework course. Yep.
Hello. Going back to one of your first slides, you define a real-life object as something that we can know something about.
Yes.
I think that's a definition that's too broad, because, for example, you can know something about the British monarchy, but the British monarchy is not an object. Or you can know something about flying a plane, but flying a plane is not an object. If that makes sense, yeah.
Yeah, okay, I agree. When I put up that definition, it was more to say, okay, how we identify objects as people, as opposed to how we define it programmatically, which is an instance of a class. Yeah, yeah.
Sorry, surely the British monarchy is just an instance of the monarchy class?
Hi. I'll just expand on the composition thing. Basically, it's just classes within classes. Well, if you have private data inside the class, it's that could be integers, doubles, or arrays of stuff.
Yes.
Composition is basically just a more advanced data member. So there's nothing really fancy about it. It's just a data member that is used for composition.
And a class is just a custom data type, such as a cluster.
Exactly. And it has a system that's called aggregation that's closely resembling it.
Yeah, I mean, aggregation, you could say, is a class uses a class, but those two can work independently. And when one dies, the other doesn't have to. Would you agree, Alan? Excellent.
With your composition,
yeah.
So the class that's within the class, is that by definition private to the class it's in, or it can be used publicly by other classes? So your serial communication, could it be used by that class, but also used by some other process somewhere else?
No. So the instance of it, it's the private data, which could be an object. That object can still only be used by methods within that object's class.
Private too.
Yeah. So it's still private. If you wanted to open it up, there are other access scopes available. I haven't seen a need to use the other access scopes, like community.
I think the question might have been, could you use other objects instantiated from that same class in other parts of your application?
Yes. Cool. Okay, my time's up. Thanks, everyone.